Imagine a natural disaster so completely devastating that it levels whole landscapes, just stripping forests down to ash and blackened trunks.
Right, absolute destruction.
Exactly. But instead of being this apocalyptic end to the environment, it's actually the starting gun for life.
Yeah, it's completely counterintuitive.
It really is. And that paradox is at the heart of our deep dive today. Welcome in, everyone. Our mission today is to unpack this fascinating collection of research that argues basically to fundamentally understand the Australian continent, you literally have to understand fire.
Yeah, you really do. And to grasp what's happening there, you have to hold two contradictory truths in your mind at the exact same time.
Right.
On one hand, fire is a deadly, catastrophic hazard to human life. I mean, it's genuine danger. But on the other hand, it is a deeply necessary ancient ecological force.
Which is wild to think about.
It is.
Yeah.
But holding both the ecology and the hazard together, well, that's the only way to make sense of the Australian bush.
Because we usually think of a forest fire as an interruption of life, right? Like nature acting against itself. But the source material paints this picture of a landscape that is quite literally built to burn.
Built to burn, yes. Perfectly put.
So to figure out why Australia is so uniquely fire-prone, we have to look at the physical environment first. The continent acts like this giant terrestrial kiln.
Oh, absolutely.
The arid winds sweeping across the interior, they don't just warm the vegetation, they actively suck the moisture right out of the cellular walls of the plants.
And that process essentially cures the landscape.
Cures it. Right. It's like drying meat or leather.
Exactly. You end up with millions of acres of living flora just baking in the sun, turning into this massive expanse of ready-to-ignite fuel. But, the climate is only the ignition source.
Right, the setup.
Yeah. The real story is the biology itself. Specifically the dominant plant of the Australian bush, which is the eucalypt, or the gum tree.
Okay, let's unpack this, because the eucalypt doesn't just passively exist in a dry place. The sources say it actively engineers its environment to be more flammable.
It does. It's essentially a gas station disguised as a tree.
A gas station. Wow.
Yeah. I mean, the leaves are packed with these highly volatile organic compounds, those aromatic oils that give eucalyptus its distinct, medicinal scent.
Right, like cough drops.
Exactly. And under the intense baking heat of an Australian summer, those oils don't just stay trapped inside the leaf. They actually vaporize.
Wait, they turn into gas?
They do. They release into the surrounding air, creating this highly combustible, invisible cloud of hydrocarbon gas hovering right there in the canopy.
And just for anyone listening, the canopy is that upper layer of the forest's leaves and branches, right?
Right, the very top of the forest. And if you've ever looked out over the Blue Mountains near Sydney and seen that famous hazy blue tint in the air.
Oh yeah, that beautiful blue haze.
Yeah, you are actually looking at thousands of tons of atomized eucalyptus oil refracting the sunlight.
That is terrifying. So you basically have a forest enveloped in its own flammable vapor.
Exactly.
And below the canopy, the eucalypt is constantly shedding, right? It dumps a massive volume of dead leaves, twigs, bark just directly onto the forest floor.
Yeah, building a dense bed of dry kindling right at its own base.
It's basically piling up its own fuel.
It is. And the bark itself is the critical mechanical link here. Many eucalypt species have this long, stringy, or ribboning bark that literally peels away and hangs off the trunk in loose strips.
And in the source material, fire scientists call this a ladder fuel, right?
Trailer fuel, yes.
Which is such a visceral term. It provides a literal pathway for the flames to climb. It's like a perfectly engineered matchstick. If a lightning strike or a dropped match ignites that dry leaf litter on the ground, the fire doesn't just stay on the ground.
No, not at all.
That stringy bark catches, acting like a literal fuse, and just carries the fire straight up the trunk into that vapor-rich canopy we just talked about.
And once the fire reaches the canopy, the behavior of the blaze changes entirely. It transitions from a surface fire into a crown fire.
Meaning it's up in the tops of the trees.
Yes. Leaping from treetop to treetop with a speed and intensity that, frankly, defies imagination.
Okay, but here's where it gets really interesting. If these trees act like giant torches building their own funeral pyres, why isn't the entire continent just a permanent, sterile wasteland? Wait, so plants don't just endure these fires, they actually exploit them. Does that mean putting out fires could actually be bad for the ecosystem?
What's fascinating here is that, yes, absolutely, if you completely suppress fire, keep it out of the Australian bush for a few decades, fire-dependent ecosystems actually begin to suffocate and collapse.
They collapse without fire.
They do. They rely on that periodic intense heat to complete their reproductive cycles. Over millions of years, the flora there evolved mechanisms to weaponize the flames against competing species.
That is just wild. Walk us through the mechanics of that survival, though. How does a living organism survive being incinerated in a crown fire that burns at, what, 1,000 degrees Celsius?
Well, the primary defense mechanism involves what botanists call epicormic buds.
Epicormic buds.
Right. These are dormant shoots hidden deep beneath the thick, woody bark of the eucalypt. The outer bark acts as a highly effective thermal insulator.
Almost like biological asbestos.
Yes, a great analogy. When a massive fire sweeps through, the intense radiant heat scorches away all the foliage and leaves the outer trunk completely charred and black.
But the inside is safe.
Precisely. The inner vascular tissue is untouched. Shielded by the bark, those epicormic buds sense the sudden loss of the canopy and the sudden influx of sunlight.
Because all the shade is gone.
Exactly. And within weeks of a devastating fire, these blackened charcoal-like trunks will suddenly burst with fresh, neon green foliage.
Oh, wow. So the trees look fuzzy, right? Entirely covered in vibrant new shoots growing directly out of the burnt wood.
It's a really striking visual of resilience. But, the epicormic buds are just for the trees that survive the heat. Some plants in the Australian bush employ a strategy where the parent plant actually dies in the blaze.
Oh, really?
Yeah, it dies, but uses the thermodynamics of the fire to launch its next generation.
Right. We see this with plants like Banksias, according to the research. They produce these dense, woody seed pods that are sealed completely shut by hard, waterproof resins.
Loctite.
Yeah, these pods can sit dormant on the branches for years, just locked vaults holding the seeds, and they literally require the extreme physical heat of a bushfire to melt the resin.
And once the fire passes, it's amazing, the pods audibly pop open, you can hear it, and they drop their seeds right onto the cooled ash.
And the timing is strategically perfect, isn't it? They
Yeah.
drop the seeds onto soil that's just been freshly sterilized of disease.
Fertilized by the ash.
Right, and completely cleared of any older competing plants that would block the sunlight.
The fire essentially clears the real estate.
But the source text points out an adaptation that goes even deeper than heat. It goes down to the molecular chemistry of the smoke itself, which blew my mind.
Oh, this is one of the most remarkable discoveries in botanical science. Certain native seeds can lie dormant in the soil for decades.
Decades.
Decades. And they won't germinate. And by germinate, I mean waking up and sprouting. They won't germinate if you water them. They won't germinate if you heat them.
They are chemically locked.
Exactly. They only break dormancy when they are exposed to highly specific chemical compounds found exclusively in plant smoke.
So the smoke isn't just this toxic byproduct of combustion, it's actually a chemical messenger.
Yes. Scientists have isolated these compounds and named them kerikins, which is derived from an Aboriginal word for smoke.
Kerikins.
Right. When smoke from a bushfire permeates the soil, the kerakin molecules bind to specific receptor proteins within the dormant seed.
Like a key in a lock.
Exactly like a key. This binding action fundamentally alters the seed's genetic expression, unlocking it and signaling the embryo to start growing. Without that specific chemical key provided by the smoke, those seeds would simply sleep in the soil until they died.
Okay, so if the landscape is basically a ticking time bomb of eucalyptus oil, ladder fuels, and seeds that are literally waiting for smoke, the fact that humans haven't just survived in this environment, but thrive for tens of thousands of years implies they found a way to disarm the bomb before it goes off.
That's exactly it. Aboriginal Australians didn't just survive the fire, they absolutely mastered it. For over 60,000 years, they have managed the landscape using a highly sophisticated, localized practice.
Known as cultural burning, right? Or fire stick farming.
Yes.
So what was the purpose of this? Because they aren't just, clearing brush to prevent big fires. They're actually curating the landscape, almost like farming with a matchbox instead of a plow to cultivate specific resources.
Yeah, and if we connect this to the bigger picture, modern land management is actively researching and learning from these deeply cultural, long-standing practices today, because the precision involved is just staggering.
Walk us through that precision.
Well, cultural burning is not about indiscriminately torching a hillside. Aboriginal fire practitioners read the microscopic conditions of the environment.
Like what kind of conditions?
They assess the moisture content of the soil, the dew point on the grass, the subtle shifts in wind direction, even the breeding cycles of local animals.
So they are essentially calculating the exact thermodynamics of the fire before they even strike a spark.
That is entirely accurate. When conditions are perfect, they introduce fire to the landscape. And these are remarkably slow, cool burns.
Cool burns.
Yeah, the flames might only reach a few inches high. They just creep through the undergrowth, gently consuming the dry leaf litter and dead grasses without ever generating enough heat to scorch the canopy.
Or ignite those volatile eucalyptus oils up above.
Exactly. The fire moves so slowly that insects and small reptiles can simply walk ahead of it to safety.
Which is incredible. And the result is this mosaic of different vegetation stages, right? You burn one small patch this year, another patch next year.
It breaks up the continuous tracks of fuel.
Right. It encourages the growth of edible plants that attract grazing animals like kangaroos, and it fundamentally prevents that massive accumulation of kindling that leads to those uncontrollable infernos.
And that's why modern fire ecologists recognize that this deep, localized understanding of fire behavior really offers a blueprint for living safely in a highly flammable environment.
Okay, but this brings up a huge question. If this localized, low-intensity burning is the historical baseline for how humans manage the land, what mechanically changes on those days when a fire transforms into the apocalyptic mega fires we see dominating the news?
Right. What goes wrong?
Yeah, what overrides those natural and human safeguards?
Well, fire scientists look at a very rigid formula to understand catastrophic bushfire behavior, and it comes down to three things: fuel, weather, and terrain.
Fuel, weather, terrain.
Okay? When all three align, the physics of the fire become almost unstoppable.
Well, we've established the fuel, the massive fuel loads of stringy bark and vaporized oil, but the weather acts as a multiplier, doesn't it?
A massive multiplier. When scientists refer to fire weather, they are looking at a specific convergence. You have high temperatures, single-digit humidity, and gale-force winds.
And the wind is the real killer there.
Oh, absolutely.
Eh.
The wind acts like a blast furnace. It forces this massive influx of oxygen directly into the combustion zone, driving the temperatures up exponentially.
No.
The heat can actually become so intense that a large bushfire will break through the troposphere and create its own weather system.
Those pyrocumulonimbus clouds, right?
Yes, fire-generated thunderstorms. The massive updraft of heat sucks in surrounding air, creating violent, localized winds.
And the ash column can generate dry lightning, which strikes the ground and starts even more fires ahead of the main front.
Exactly. But even without dry lightning, the wind performs a terrifying mechanical action known as ember attack.
Right, the spot fires.
Yeah.
Which fundamentally changes how we need to think about a fire approaching a town. It's not this slow-moving wall of lava that you can just casually outrun.
Not at all.
The wind picks up burning pieces of that stringy eucalyptus bark, carries them high into the convection column, and hurls them miles ahead of the actual fire line.
And those burning embers just rain down on unburnt forest or, tragically, onto the roofs and gutters of homes, igniting hundreds of new, independent fires.
Which are what we call spot fires.
Right. An ember attack is literally like a blizzard of fire.
Right.
People often believe they are safe because the main fire front is, say, 20 miles away.
Because they can't even see the flames yet.
Exactly. They are completely unaware that an ember has landed in their backyard and ignited a spot fire that will trap them within minutes.
It's terrifying. And the final variable in that disaster formula train dictates how fast that trap closes, right? Fire behaves wildly differently depending on the topography.
It does. Fluid dynamics dictate that fire travels significantly faster uphill than it does on flat ground.
Yeah, a really good everyday analogy for this to help visualize the mechanics is to imagine holding a lit match under a flat piece of paper. The heat rises vertically and the flame burns at a steady, predictable rate.
Right.
But if you tilt that paper onto an angle, mimicking a steep hillside, the flame is suddenly leaning directly against the unburned paper above it.
And the physics of that tilt are deadly. The radiant heat from the flames physically preheats the slope directly above.
It bakes the moisture out of the vegetation before the fire even reaches it.
Exactly. So by the time the actual flames arrive, the fuel is already at its ignition point. Because of this preheating effect, a fire can race up a steep mountain slope with terrifying velocity.
Easily outpacing wildlife, firefighters, vehicles, everything.
Everything.
So what does this all mean? Since we cannot flatten the mountainous terrain, and we certainly can't turn off the gale force winds, the only variable in that disaster equation we have any operational control over is the fuel.
Correct. Which brings us to the modern industrialized equivalent of cultural burning, which is hazard reduction or prescribed burning.
Right.
Fire authorities utilize the cooler, wetter months of winter and early spring to deliberately ignite sections of the bush under strict parameters.
The objective being to consume the accumulated leaf litter and surface fuel in a controlled manner so it's not there during the summer.
Exactly. The logic being that if a fire does break out on a catastrophic summer day, it will eventually hit that prescribed area. With the surface fuel already gone, the fire drops out of the canopy, loses its intensity, and gives firefighters a tactical window to suppress it.
But the source material is highly explicit about the limitations of this strategy. It is not a cure-all.
No, not at all. Prescribed burning is a critical tool, but it is bound by severe logistical constraints. First, the weather window to safely conduct a burn is incredibly narrow.
Because the vegetation has to be dry enough to actually carry a flame, but the air has to be cool and still enough to ensure the fire doesn't escape containment.
Right. It's a very delicate balance. Second, the bush regenerates rapidly, meaning the protective effect of a prescribed burn diminishes significantly within just a few years.
The fuel just grows right back.
It does. And perhaps most critically, on the absolute worst fire weather days, when you have temperatures above 40 degrees Celsius and 100-kilometer-per-hour winds, the weather simply overrides the fuel reduction.
The wind will just drive a fire straight through an area that was treated with prescribed burning just months prior.
Yes. And this is where the shifting climate radically complicates the math. The most rigorously established scientific trend regarding Australian bushfires is the lengthening of the fire season and the increased frequency of dangerous fire weather days.
Because warmer average temperatures mean the landscape dries out much faster in the spring and stays dry much later into the autumn.
Exactly. And that underlying temperature shift mechanically shrinks the safe window for prescribed burning.
Right. If the winter is unusually warm and dry, fire authorities lose the specific micro-conditions required to safely burn off the fuel loads.
So they are forced to enter the summer fire season with heavier fuel loads than planned. This raises an important question about how we talk about climate change and fires.
Right, because when analyzing the intersection of climate change and natural disasters, precision is vital. The science doesn't point to a single bushfire and declare it was manifested out of thin air by climate change.
No, because as we've discussed, fire is a deeply endemic feature of the continent.
What the climate data reveals is a statistical shift in the underlying conditions. It's basically the statistical equivalent of loading a pair of dice.
Oh, that's a good way to put it.
Yeah, if you walk into a casino with loaded dice and roll snake eyes, you can't definitively prove that specific roll was caused by the hidden weights. Natural probability dictates you could have rolled a 1 and a 1 anyway.
Right, fires happen.
Exactly. But if you sit at that table and roll the dice 1,000 times, the underlying weights guarantee you will roll snake eyes at a frequency far beyond natural variance.
Yes. The changing climate is loading the dice for extreme fire weather, guaranteeing that the atmospheric conditions necessary for megafires align much more frequently.
And a longer season with more frequent extreme weather days means the margins for error in human settlement and land management are continually shrinking. The historical baseline is just moving.
It's moving fast.
So as we wrap up this deep dive, it's clear the story of the Australian bushfire challenges our fundamental desire to conquer or sanitize nature. We look at the devastation and instinctively want to eliminate the threat.
Which is a natural human reaction.
Of course, but a continent like Australia can never eliminate fire. Fire is not the enemy of the landscape, it is the architect of the landscape.
Absolutely.
It is woven into the cellular biology of the trees, the reproductive cycles of the seeds, and the ancient cultural practices of the people. By understanding the intricate mechanics of how it operates, respecting both its ecological necessity and its terrifying physics, we can adapt our architecture, our land management, and our expectations to live alongside it more wisely.
I want to leave you with a final thought to mull over, returning to the molecular chemistry we discussed earlier.
Oh, the smoke seeds.
Yes. Consider the implications of kerikins, those specific chemical compounds in smoke that unlock the dormant seeds in the soil.
Right.
Scientists are actively mapping these molecular structures. What happens when we can fully synthesize those chemicals in a laboratory?
Wow, wait.
Yeah, we could theoretically manufacture a synthetic smoke, a chemical trigger that could be applied over vast tracts of degraded, dying forests worldwide.
Just bypassing the fire entirely.
Exactly. We could initiate mass ecological regeneration, waking up billions of dormant seeds and restoring collapsed ecosystems, all without needing to spark a single flame.
That is incredible.
It really is. It completely recontextualizes our understanding of smoke, transforming it from a suffocating byproduct of destruction into a master key for biological life.